Oh, Luke, the first thing to note about this question is that I think there's a typo. So I'm going to go with replacing perimeter by arc length, which matches the solutions, but it also makes life a lot easier as well. So our next bit is to remember what the equations for arc length and later on area of a sector are. So the first one is that a sector is this shape here with an angle theta, radius r. The arc length is a fraction, so theta on 360 is the fraction of a circle that you've got of the normal circumference of a circle. And the area of the sector is again the fraction of a circle that you've got multiplied by the area of a full circle. So then we go to the question and identify what we've been told. So the arc length of the circular sector is 20 centimetres and the radius is increasing at 5 centimetres per second, so that's dr dt. Then we identify what we want, which is the rate of change of the angle. So we know that's d theta dt, and we want that when r equals 10 centimetres. And now we set up our chain. So when we set up the chain, we've got this and, sorry, we want this, we've got this, so we need this, which we need to have a relationship between theta and r to be able to find. And that's this one here, as long as the length is fixed, and we are given that as 20. So we need to rearrange this and then differentiate. So when we rearrange this equation here to make theta the subject, then we've got this, and because we're going to differentiate with respect to r, this is the variable and this is a fixed value of 20, so we just write it as r to the minus 1, which gives us this thing here, and I've just substituted in the value of L as 20, and now I'll put in the value of R, which is 10, which takes us, when we plug that in, to minus 36 on pi. So the angle is actually decreasing, and that's because the perimeter has to stay the same if the radius, so we were told it had to be 20. So if the radius is increasing, this sector must be actually getting narrower. So now we come back and we just finish off the chain rule. So we get minus 180 pi degrees per second as d theta dt. Now for our second part of the question, we want the rate at which the area is changing at a certain value of radius. So again, we identify what we've got, what we want, and then we need to set up the chain. So we can see that what we want is dA dr, which means that we need the link between A and R, and we have this up here. So from this bit, if we get dA dr, so dA dr equals this, so here's our differential here. I've plugged in our value of R as 10. That will obviously simplify down just a little bit, but we need a value for theta. Otherwise we've got another variable in here. So we've got to find the value for theta when the radius is 10. So if we go back to our original connection between radius and the perimeter, or arc length, as I said, this was this equation, so we know that. So we can work out what theta must have been at that instant. So now that we have this value of theta, if I take this and put it back up into dA dr, so when we take this and plug it into here, then fortunately these things cancel out, so we're just left with dA dr equals 20. So dA dt works out to be 100 square centimetres per second.